are studying for the exam, there's this study guide document. It's at the top of the page where I post all my lecture recordings. It includes some references to places that you're going to find additional practice problems. So if you're looking for more practice problems, that's a good place to go. I think overall, one of a good approach would be to say, okay, for every problem I look at on the exam, first, I need to quickly identify the problem type. Is it equivalent system? Is it a rigid body equilibrium? And then second, know the general steps to solve that type of problem. If you know the steps, you're going to have enough time to finish that exam. If you're kind of fuzzy on those steps, let's work on that and get you to that point where you're going to have enough time to finish all those problems on the exam. And then once you identify the steps, then pictures, what I mean by pictures is mostly FBDs, and then the equations to solve for those unknowns that we're looking for. Okay, any questions about our upcoming exam here? Okay. All right, let's go into frames. So analysis of frames, which is not on the exam, but we're going to continue expanding really our knowledge about some of the things that will be on the exam. So it's kind of like they're just, more complicated problems. And so if we can look at these frames a little bit before the exam, certainly not going to hurt. And so one of our learning objectives is explain how a frame is different than a truss. So we're already comparing it to something that we've done before, and so it'll solidify our understanding of trusses. Identifying two-force and multi-force elements. We actually already had this learning objective before, so this is, this is something that we will solidify our understanding of. I see a question here, how many, about the exam, how many questions? There will be 20 questions, just like the first exam. The third learning objective, know what reaction forces occur at a pin when we have a two-force and a multi-force element, and a pin connecting a multi-force and a multi-force. We'll solidify our understanding of that, which we have talked about before as well. And then identifying and drawing the FBDs that will allow us to solve for those unknown reactions, key for these problems and other problems that we've talked about in the past. And then the equations of equilibrium, that's really the easy part, right? That's what we've been talking about all semester. Some of the forces is equal to 0, and some of the moments is equal to 0. Sometimes my wife jokes with me and is like, why do you have to teach statics like all semester? Don't you just like make the sum of the forces equal to 0 and like everything is, and then you're done, right? So you just like throw up a, sum of the forces is equal to 0 and you just leave it up there the whole time? Like, no, that's not what we do in statics. Okay, so for our homework problems, and this isn't due until after the exam, what a frame really is, and we'll write this down, is that we have at least one multi-force member. We can still have two force members, but we have at least one multi-force member, and so we need to find the reactions at the pin support E. So we see all the same types of connections that we've seen before. We're just going to have problems that have many more members, many more rigid objects in them. And really what that does is it means that we have a lot more options for FBDs. And so picking that FBD is going to become even more important with these types of problems. Our second one, we're asked to find the reactions at A and D. I'm going to see some pulleys start showing back up. We'll talk about how we handle those. Notice again, there's two different rigid objects in that homework problem, and then homework problem number 3, 2 rigid objects, a little bit more stuff going on, and we're asked to find the reactions at A, B, and C. We're going to come up with a really nice way to solve these problems, and it's all about being able to identify all the free body diagrams, and if we can identify all the free body diagrams, then we can pick the correct FBD. And that's what this problem is really about, is to think about, okay, well, where are my possible FBDs? Well, I could do an FBD there, and what are the correct forces in there? Or we could do an FBD here, or we could do an FBD here, and looking at all those different FBDs and picking and figuring out, okay, which one am I going to use first, second, and third? Okay, so actually before we get to an example, on the board here for our frames, let's write down just a couple of key things. One of our first learning objectives was to compare this to trusses. So as compared to trusses, we have at least one multi-force member, which is a member. Anytime I say member, that means a rigid object. So at least one of our rigid objects is going to be a multi-force member. And our FBDs for this one, with trusses, we had joints and we had sections. Our FBDs are going to be of the individual member or of groups of members. And we cannot make any cuts through multi-force members. So that's why we draw an FBD of an individual member, the entire individual member. So no cuts through those multi-force members. We have made cuts through two-force members. That's what we did with trusses. That was method of sections. We were cutting through those two-force members. With frames, though, we are going to make sure that we are not making any cuts through multi-force members. We can cut through two-force members, but not through multi-force members. And our best practice for picking FBDs is what I refer to as complete. Let me spell complete first. Let me finish completing complete. Complete enumeration. Of all options. So what that means is we need to identify all of our free body diagram options, and then we can go through them and just look at them individually and say, what about this one? What about this one? What about this one? So let's start this by looking at example 6.9 from your textbook. And example 6.9 has two rigid objects. It's got a rigid object here, and there's a hole down here, and there's a hole up here. Let me zoom in a little bit here. It's easier for me to write when I'm zoomed in. And there's another rigid object here that goes down, and there's a pin there, there's a pin here. So we have a pin connection up here. And then down here at point A, this is a pin support. And so we can draw one of those like triangle looking things, right? So there's a pin support right there. We have another pin support down here. And so we'll label this points A, B, and C. And we have let's apply a couple of forces and moments to this thing. What if I applied a force here in between B and C? And we're just going to we're going to do this whole example just symbolically. I'm just going to call that a force P right there, and it's applied in between B and C right there. What type of member is B to C? Is B to C a two-force or is it a multi-force? Let me call on somebody from the front row here. How about Audrey, Richard? B to C is what type of member? Is it a two force or is it a multi-force? Okay, how about is Hayden? How about Hayden Payne?
Yeah, I think, is it a two force member?
B to C is a multi-force because there's more than two locations where forces occur. So right now B to C is a multi-force because we have forces at B because that's a pin connection. And what do we have at a pin connection? We can have like an X and a Y, or there is a force at the pin connection at B. There's also a force or more than one force at the pin support at point C. So there's 1, 2, 3 locations of forces. So B to C right now is multi-force. Now, how about A to B? A to B right now is a two force or a multi-force. Hayden, again, go ahead.
This one looks like a two force. I was missing the P, I suppose.
Yeah, no, that's totally fine. That's why we ask those questions during class. Yeah, A to B is a two force member because there's only two locations. Okay, now I'm gonna add one more thing. I'm gonna add a moment here. And so there's also a applied moment right there. So we have an applied M and we have this applied P to our system. A to B, when I didn't have M, was a two force. But now that I've applied a moment, both A to B and B to C are now both multi-force members. Okay, so what we're going to do is we're going to come up with a way to solve this problem. So let's look at all the possible FBDs or complete enumeration. So let's identify all possible FBDs for this problem. Well, actually, I have a physical demonstration of this example too. So here's A to B, right? And here's B to C. And so it's literally, they're just connected by pins. So I have a pin down here at this point, right? I have a pin over here at this point right here. And then there's just a pin connection right there, which is literally just a pin going through a hole in those rigid objects right there, right? And so if we think about all of our possible FBDs, well, we can do an FBD of the whole thing. And that would basically mean just pulling out the pin down here and pulling out the pin over here, but leaving the pin up here intact. We could do an FBD of this member just all by itself. So separate it out and we can do that FBD. And then we separate that one off and we'll do an FBD of that one. So we have two members, we have two rigid objects in this, but we have three possible FBDs. So let's look at, to start with here, why don't we do an FBD of the whole? And so when we do an FBD of the whole thing, what we're talking about is we leave stuff intact up there at point B. We've got our applied loads here of a P and an M over here, and I don't really care exactly where M is applied. It looks like it's applied pretty much at A. We can assume it's applied pretty much at A. And so B, everything up here at B is internal. Nothing, I didn't remove that pin, kind of like with trusses. If we didn't cut through a truss member, well, it didn't matter what was going on there. We didn't expose those forces. Well, same thing at this pin, we left it internal. And so there could be 1,000,000 pounds in there, or there could be 0 pounds. It doesn't matter because we didn't expose those. Now, A, the pin support at A and at C, we did expose those. And I'm going to draw, because it's a pin support, it can resist translation in the Y direction and in the X direction. I am not worried about what direction I'm drawing those in. My math will tell me if they go in the opposite direction. So I'm just picking. AY is going to go up and AX is going to go to the right. And then over at C, again, a pin support. It prevents things from moving in the X direction. So I'm going to have a CX. It also prevents things from moving in the Y direction. So I'm going to have a CY. There is no moment reaction at A or C because they're pin supports, they allow, right, this right here, that pin support allows rotation from happening. It doesn't allow it to translate in either direction, and so I have an X and a Y force at those two. Okay, so our FBD of the whole system here, we look at that, and there's actually, assuming we know M and P, right? So let's say, this is a known M, and this is a known P over here. We have 4 unknowns. Now, we only have 3 equations of equilibrium. If we're in 2D, we have sum of forces in the X, sum of forces in the Y, and we have sum of moments. We'll talk about how we solve these later. Let's continue on for now with our next FBD. Let's do an FBD of A to B. And it doesn't matter, I'm not going in any particular order for looking at my FBDs. I just want to be able to identify all the possible FBDs and to draw them correctly as well. So now I'm going to do this one. I did the last FBD of a hole as just a wireframe, right? I just did a line without a thickness, those black lines there. Let me do this one as like with a little bit of shape to it, like the original picture shows us. Now, AX and AY we had already drawn. This is one thing we have to watch out for with frames when we're looking at multiple possible FBDs, is that we don't want an FBD to contradict another FBD. Like we want to make sure that when we pick a direction for AX, we're consistent with that direction. So we picked AX to the right, so we better make sure that this is the same force that we're exposing for the FBD of the whole and the FBD of just A to B. And so we want to make sure that we draw those in the same direction. Okay, so we have AX and AY. We have our known M that's applied to our system there. And then up here at point B. At point B, what's really going on is when we separated this out, is we had a force between these 2 rigid objects. And so we have a pin connection right there. This is a pin connection between 2 multi-force rigid objects. Remember, we identified this one as rigid or as a multi-force. This one is also a multi-force rigid object. So anytime we have a multi connecting to a multi, it's going to be an X and a Y. The other thing that we can have happen is if it's connected to a 2-force member, well, then we know the line of action. But for frames, it is, we have a multi and a multi for this example. So it's going to be an X and a Y. I haven't drawn BX anywhere else, so I'm just going to go ahead. I'm going to draw BX to the left, and I'm going to draw BY down. So I get to pick. I'm just arbitrarily picking here a BX and a BY direction. Doesn't matter. I could have drawn them in the other direction, and that would have been totally fine. Okay, let's go ahead and let's draw our last FBD here. And that's going to be an FBD of B to C. Now B to C is this rigid object here. We know we have this known applied force of P. At C, we have already drawn it here, CX and the CY. I'm exposing those same forces, so CX needs to go the same direction as I already drew it. CY needs to go the same direction as I already drew it there as well. And so there's our CX and our CY. Now up here at point B, I've also drawn those somewhere, but I'm on the opposite side of that connection as to what I drew them in AB. So these forces up here, let's go back to the FBD of A to B. This BX and this BY up here, these are the forces from B to C acting onto A to B. So when we draw them down here, these are going to be the forces from A to B acting onto B to C. So they're going to need to go in what direction? What direction should BX go on my FBD of B to C? Let me ask Ricardo. Ricardo, what direction should I draw BX? Should I draw it to the left or should I draw it to the right?
To the right.
To the right, because I drew it to the left in the one up there, so I need to draw it in the opposite direction. So anytime we're looking at FBDs that are on opposite sides of that pin, our forces, our reaction forces, they always should go opposite directions. So BX is going to go to the right, and BY is going to go up. Thank you, Ricardo. We can also think about this with our physical demonstration here. If we think that, okay, let's see, and this is kind of, I feel like things are backwards for me on the screen here. So let's just say if this one is causing a force this way, right? If this member here is causing a force this way on this one, then this one has to be causing a force in the opposite direction on that one there, right? And so we can think about this in terms of like the physical phenomenon that's happening. Or if you think about it like in terms of like tug of war, right? If we're playing tug of war and I'm pulling on you, well, you're also pulling on me. So relative to you, the force is going to be coming towards me. But relative to me, I'm going to feel a force going towards you. And so it's that same idea at these connections when we draw an FBD on one side of the pin and an FBD on the other of the rigid object that's on the other side of the pin. Okay, now how are we going to solve this problem? What equations can we use to actually find solve for our unknowns? And how many unknowns do we have in our problem here? We have an AX, we have AY, we have a BX, we have a BY, and we have CX and CY. So in all together, we have 6 unknowns for this problem. In each FBD, how many equations do we have? Anyone? How many equations do we have for each FBD? Not 6, that would be in 3D. In 3D, we can have 6. We can have moments around all 3 axes and forces on all 3 axes. We have 3, yes. So, and I should have called on you because you're in the front row today. So yeah, we have 3. We have 3 equations that we can use for each FBD. So technically, we only need 2 of those FBDs because we can solve for 3 on one of them, and then we can solve for the other 3 on another FBD. There is only, though, one place to start solving this problem. And let's just go through this, and let's look at each. I'm going to go backwards. Let's go backwards. If we look at each FBD, they all have 4 unknowns in it. The B to C FBD, it has BX, BY, CX, CY. That's 4 unknowns. The A to B has 4 unknowns. AX, AY, BX, BY. The FBD of the whole has 4 unknowns. AX, AY, CX, CY. Now, if I start thinking about, okay, what's my more powerful equation? My more powerful equation is the moment equation because I can get rid of unknowns by picking a point with lots of unknowns, right? So for example, if we looked at the FBD of B to C, what if we did the sum of the moments about point C? Oh, that's still going to have a BX and a BY. What if I did the sum of the moments about B? Oh, that's going to have a CX and a CY. At A, what if or up here in A to B, what if I sum moments at A up here? Well, that's going to have a BX and a BY too. And we could start doing like, coming up with 2 equations here and 2 equations there. But let's go through all of our FBDs. Ideally, I want to find one equation with 1 unknown. So we're still looking to do that. So right here in the FBD of the whole thing, if I look at summing moments about A, how many unknowns am I going to have when I sum moments about point A? Anyone? just cy. Absolutely, and that's because A and C are in a horizontal line, so CX goes right through point A. So we're gonna, number one, we're going to sum moments about A equal to 0, and we'll, and actually let me write which FBD we're using first. So number one, we're gonna do the FBD of the whole, but you can see that we needed to identify all of our options first, right? Then we can pick which FBD we're gonna use. FBD of the whole, we'll sum moments about A, and we'll find CY. Number two, we can actually, from all still in the FBD of the whole, we can sum forces in the Y equal to 0, and we can find AY. So we just found AY, and we just found CY. We found that, and it's only one equation with one unknown, which is really cool. And then our second, number two, that was only one equation with one unknown also. So even though you look at like, oh, we might have all these system equations, no, let's try to avoid that. Let's find, sometimes it's unavoidable, but we're gonna try to find those first. What can we do now? What's our next step that we can do? James Salazar. Any ideas? Where should we go next? Oh, James. Okay, let's Madison. Nope. And Enzo. Enzo, any ideas?
What was the question?
What should we do next? What should step number 3 be? I'll give you a hint. We can't do anything with FBD of the whole anymore. We've found two things, but we're not going to be able to find CX or AX right now.
Would we do a FBD at A for?
We can do. Yeah, what FBD should we use? Should we do A to B or should we do B to C?
A to B.
A to B, absolutely. Actually, either one of those would work. Think about this. If I do the FBD of A to B, I know AY. How many unknowns do I have here? I have 3 unknowns. I have AX, BX, and BY. If I do the FBD of B to C, I have CY, so I only have 3 unknowns in that one. So actually, once we figure out that first FBD, these problems usually have multiple paths to finish. But at that first one, there was only one first step that was going to work for us to have at least one equation. There's other ways to do it, but like a nice, easy mathematically, like not a lot of algebra. The FBD of the whole gave us that one equation with one unknown. And now we're into like a bunch of like one equation, one unknowns here. So yeah, either an FBD of A to B would work, like Enzo suggested. And so FBD of A to B, we know AY. So couldn't we, like, we can just think about our equations as options now too, and just going through our options, like sum of forces in the X. Oh, that has 2 unknowns. Sum of forces in the Y. Oh, that works. Let's do sum of forces in the Y. We would find BY for that one. And then we could keep going here. Number 4, we could do FBD. We'll still stay on A to B because we can solve for all this stuff. And like we can do some of the, how could we find, we know AY, how could we find AX? We could find AX, couldn't we do some of the moments about B equal to 0? And that would allow us to solve for AX. And then we could do some of the forces in the X equal to 0, and we could find BX. And then number 5 here, we could go back to the FBD of the whole. And we could, now that we know, let's see, now that we know AX, Now we can do sum of forces in the x is equal to 0, and we can find Cx. And so now we've solved for all of our unknowns. So complete enumeration, identifying all of our possible FBDs, making sure we draw them correctly. There are no other FBDs that we would consider for this problem, right? We would never consider like point A. We're not doing that. We have to do, remember, our FBDs are of the entire individual members or groups, right? Our FBD of the whole, that's a group. That's both of those together. And then we did an FBD of AB, FBD of BC. Those are all of our FBDs. There are no other FBDs for this problem. And then I see, could you use the FBD of BC to find CX? Yeah, we didn't even use BC, but we could have used BC. Starting here at step number 3, we could have done BC instead of AB, or we could use all 3 FBDs. We could do AB for some stuff, and we could use BC for other things. Okay, so how about applying that to problems that look a little bit more like the problems in the homework? Again, let's think about this. We're not going to solve this problem. We're going to solve a different problem. But let's think about this in terms of identifying all of our rigid objects. And then that's our possible FBDs. And so we have this as a rigid object, and this is a rigid object. We'll talk about how we deal with the pulleys, and we'll figure that out. But we still have in this, then, how many possible FBDs do we have? We could do the FBD of the whole thing. We could do an FBD of B to D, and we could do an FBD of A, B, C. So it's still this, it's like the same thing. It's just we have 3 different options for FBDs. Don't be afraid to draw each one and then figure out, okay, which one am I going to use? Again, in this one, we also have 6 unknowns, so we don't need all 3 of them. We only technically need 2 of them. Here's the solution, and this one is up on Canvas. We'll talk about how those pulleys are working here in a little bit. But like we see, I just want to use this right now, point out that it's up on Canvas in the supplementary problems, but also to point out, look at, they have 2 FBDs. They picked 2 FBDs. That's all they needed to solve that problem. Okay, so I just wanted to relate the example that we just did to what we're going to move into now. We only have a few minutes left here, but why don't we go ahead and utilize this time. This is the problem that we're going to continue solving on Friday. And so our given information here, I'm going to draw the points here first, and then I'll draw my rigid object around those points. So we have point A is there, point B is here, point C is there. Let's see, that would put point D about right there or so. And so we have this rigid object there from A to B to C. We have a rigid object that goes from here and goes around this point right there. We have a couple of pin supports here on a wall. There's a pin there and a pin support right there. And then we have some pulleys, and I got a pulley here and we have a pulley here. These are all frictionless pulleys until we say otherwise. That's going to be the case. And we have a rope that goes over this right there and comes down over here. My picture is really not looking very good, but that's fine, right? That's why we have the nice image from the textbook over here. And so then let's get some of our geometry on here. And so this is a distance of 0.8 meters. We have a distance here of another 0.8 meters. And then this vertical distance right there is 1.2 meters. They do tell us that the radius of our pulleys, that R is equal to, that's an R, not a V. The first R was the best one. Our R is equal to 0. I'm going to convert it to meters. 0.1 meters for the radius of our pulleys there. And this is 50 kilograms. So right here, this is 50 kilograms, which is 490.5 newtons. Remember, if we're given stuff in kilograms, we got to convert it into newtons there. I think that's all of the given information. And then they ask us to find the force at C on member ABC and CD. Again, in this problem, we'll look at how we deal with those pulleys, and we will also, I need to restart my computer. And then we only have 2 rigid objects. We have 2 members, and we'll identify those members and look at our drawing all of our FBDs here. You all have a great